In this video, we are going to be talking about our final simple gas law relating the volume of a gas to the amount of gas in the container. We have all blown up party balloons at some point in our lives. If we put one puff of our breath in, we might inflate the balloon a small amount, and then as we continue to blow into the balloon, then the balloon gets larger. This is assuming that the external pressure and the pressure of the balloon remains constant and that the temperature remains constant in the process as well. So as we add more gas into the container, then the container increases in size. So that's using a flexible container. So we use N here to represent the amount in moles. So our moles of gas. And then we are going to be, if we increase the number of moles, we increase the volume of gas. Much like with our other simple gas laws, there is a linear relationship between these variables. Since these are directly proportional, then we have a linear relationship between the two. So as we increase our volume, we increase the number of moles in the container. This is known as Avogadro's law. Same Avogadro as Avogadro's number that we learned about in an earlier module. Same scientist, so he got the same law. It should come as no surprise that his is the simple gas law that involves moles of gas, since he is the mole guy. He came up with the mole. So here we have this linear relationship solving for K at initial and final volumes and mole amounts. We can come up with Avogadro's law here. We have an example problem. This reads, a balloon is initially filled with 0.90 grams of CO2. So this is going to tell me my initial moles, but this is not in moles yet. That's given to me in grams. So I'm going to have to convert that into moles eventually. This is my initial pressure, but pressure is not changing. I do not see another pressure anywhere here. Cross that out. And a volume, this is my initial volume. More CO2 is added to the balloon until the volume is 1.5 liters. And so that's my V2. What is the final mass of CO2 in the balloon? And so that's going to relate to my final moles, but I'm going to need to convert that into a mass. So in order to go from grams to moles, I'm going to have to do a unit conversion. So my initial grams of CO2 will need to be converted into moles. That means I'm going to have to cancel out grams, and get into moles. That's going to require my molar mass. The molar mass of CO2 is 44.01 grams per 1 mole. You can get that by adding up 2 oxygens and 1 carbon on the periodic table. So my initial moles is 0.0020449 blah 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 moles. I'm going to go ahead and store that number into my calculator so that I can recall it later. And so if I set up my relationship here, I know that they are inversely related, and so I'm going to have them, when they're across from one another like that, that means they're directly proportional. So my initial volume was 500 milliliters. I'm solving for N2. Let me isolate N2 over here. N2 will not give me my final mass directly, but it's the variable that's most directly connected to that. So now I rearranged my equation to solve for this variable. And so I multiplied by the inverse of that on both sides. And so now I can plug in my variables, 1.5 liters, and then my initial moles was this tiny little number over here. I don't know what I pushed. And then my initial volume, where's my initial volume? My initial volume was 500 milliliters. Those units do not match. I need to make them match first. That way my units cancel. That's going to be 500 milliliters is 1/2 of a liter. So I'm going to convert them both into liters so that my liters cancel. So now my equation is 1.5 times, I'm going to recall the number that I saved. And that tells me that my final moles of gas is 0.00613 moles. That's not what the question asked for, though. The question asked for grams. And so I'm going to have to take my moles and convert that back into grams. So I have to cancel out my moles, and I have to get into grams. And so 1 mole is 44.01 grams. So I can take that and multiply it by 44.01. And so that is 0.27 grams. I need to think about sig figs. That did have 2 sig figs. That had 3. That had 2. So I do need just 2 sig figs. So 0.27 grams is a reasonable value. Now, as far as reasonability goes, we are increasing the volume by quite a bit. And so we do expect our grams to increase by quite a bit. This is times 3, our volume times 3, and we are multiplying our grams times 3. Here is a practice problem for you. Go ahead and pause the video and try to work this out on your own, and then unpause the video when you're ready to check your answer. Okay, let's go over this. It says a container with a movable piston. That tells us that our volume is flexible. Has a volume of this, that's my initial volume, and a pressure of this, that's my initial pressure, and it contains 20.3 millimoles of argon. So that's my initial moles. If an additional, that's a key word there, an additional 50 millimoles of gas is added, what is the new volume of gas? So it doesn't mention pressure again, so pressure must be staying constant. So I can erase this. So my N final here, my second N, it says additional, and so that means that my final N is going to be whatever my initial N was, plus the change. And so the change was 50 millimoles. And so that means my final N is going to be 70.3 millimoles of gas. You can see that the identity of the gas did change. This is argon and this is helium. But this ideal gas law does not determine, like, the volume will not depend on whether it is argon or whether it is helium. It just depends on how many moles of gas there is. So we can add those two molar amounts together in order to get moles of gas overall. It doesn't matter what the identity of the gas is. You just have to make sure that you are adding moles together. Don't add the grams. Add the moles. So we have our V1 over N1 is equal to V2 over N2. And so my initial volume is 0.500 liters, and my initial moles is 20.3 millimoles. That's what the mmol is. Just like any other unit, you can put a milli prefix on moles. And then we have we're solving for V2. And so my final N was 70.3 millimoles. So V2 will be equal to 0.500 liters times 70.3 millimoles divided by 20.3 millimoles. That's just multiplying 70.3 by both sides. Now I can solve for V2, and that's going to be equal to 0.5 times 70.3 divided by 20.3. So that means my final volume will be 1.7315. The millimoles cancels out. This is in liters. I need 1, 2, 3 sig figs. 1, 2, 3. That was significant to the 10th place. Yep, 3 sig figs. So V2 is equal to 1.73 liters.